Hi there, welcome to this video, which is the next in my series of videos on Richard Dedekind's essay titled The Nature and Meaning of Numbers. In this video, we're going to be taking a look at the contents of Chapter 5, The Finite and Infinite, which, relatively speaking, is quite a short chapter, but there is quite a lot to say about it. In particular, what we see in this chapter is Dedekind's attempt to characterize the finite and the infinite and how to distinguish between the two. And the definition that he gives is arguably quite contentious. So there's a little bit that I want to say about that. So I have said in a previous video that I don't really intend to go into deep critical analysis with Dedekind's work in these videos, but I will touch upon some of the problems that emerge, or potential problems that emerge from Dedekind's definition, Dedekind's characterization of the infinite. As usual, I'm going to be reading through the contents of the chapter, and I'm going to stop and I'm going to give my interpretations and explanations from time to time. I'm going to have up on the screen roughly the page that I'm currently talking about. Hopefully I'll remember to change the pages at the right time. So, okay, without further ado, let's get started then. So straight into... actually, before we start, and before I forget, if you wouldn't mind just hitting the like button to this video, subscribing to the channel, and don't forget to leave a nice positive comment in the comments section. That would be much appreciated. Okay, so let's get started then. So definition 64. So this is Dedekind's definition of infinite. And it's interesting to me to note that he defines the infinite before he defines the finite. I don't know if I'm reading too much into that. Maybe it was something, mathematicians at the time were starting to come to terms with the fact that the infinite is the more usual thing to deal with in mathematics as opposed to the finite. I don't know if that's got anything to do with it. That's just an idea that I had. But it is interesting to me that Dedekind defines the infinite first. So let's have a look at his definition then. So it's a system S is said to be infinite when it is similar to a proper part of itself. In the contrary case, S is said to be a finite system. Okay, so as we might expect, we've got this kind of falling apart of systems into two mutually exclusive categories. We've got the infinite systems, and then we've got the finite systems, which seems to agree with our intuitive expectations, let's say. But there are some issues with this. So let's just be clear about what he's saying here with the definition. So a system S is said to be infinite when it is similar to a proper part of itself. Let's just be clear about what that entails in Dedekind's work. I didn't mean to do that. In Dedekind's essay. So a system has elements, and we can apply a transformation to a system. So if we've got a system S, we can apply a transformation to this system, and we end up with a new system, which is the system of all transformed elements of S. Okay, so we apply phi to each of these elements, and we end up with a new element in what we call phi S, the transform of S, or sometimes we might write this as S prime. Okay, and it might be that S primed is itself a part of S. So this is, if we think about the terminology that's being introduced previously, this is the transformation of a system in itself. Okay, so it might be that phi S is a part of S. Okay, the two S's that I've got here don't exactly look the same, but it doesn't really make any difference. Okay, so if phi S is a proper part of S, then what we expect is that there's kind of this elements of S that are not in phi S. Okay, there's at least one element of S that is not an element of phi S, and that would mean that phi S is a proper part of S. Okay, so in the infinite case, where S is infinite, then we can have, so this won't necessarily be for every, this is relative to a particular transformation, and it has to be a similar transformation. Then we've got that phi S is a part of S. In the finite case, this can't happen. In the finite case, whenever we apply a similar transformation to S, we always get that phi S is equal to S. Okay. Obviously, if phi is not a similar transformation, then none of this is really relevant. So Dedekind has formulated his notion of infinite and finite in terms of these similar transformations, and we've got to bear that in mind. That's really important, especially when it comes to, for example, theorem 70, which I'll be looking at later in this video, which basically says that if we've got a finite system and we add another element to it, the system remains finite. Well, this seems obvious when we've got number already at our disposal, but we don't here. We've formulated the concept of finiteness in terms of similar transformations. Okay, so it makes the proof of theorem 70 potentially a bit more difficult. So what are some problems with Dedekind's definition here? Well, arguably, if we think about our intuitive understanding of finite and infinite, our notion of finite seems to be intimately tied to our intuitive understanding of finite numbers, and in natural numbers there seems to be a very close relationship between the two. And maybe on a psychological level, these two concepts are we think of them in terms of each other. Neither necessarily has, in our intuitive understanding of these concepts, neither necessarily has kind of an intuitive priority of the other. In other words, we think of finite in terms of what we think of as natural numbers, and natural numbers in terms of things that we consider to be finite. I don't know exactly, but that's a possibility. Well, obviously, from a logical perspective, if that's the way that things work psychologically, it doesn't seem to cause any problems for us. But from a logical perspective, this state of affairs would be inadmissible. Something we can't have circular definitions. This defined in terms of that, and that defined in terms of this. We can't have situations like that. Something has to be given logical priority, but which one? So we've got these two ideas that are seem to be very closely connected with each other. Which one do we give logical priority to? Well, Dedekind has given logical priority to our notion of finite and infinite. And I think there's a reason for this. When we consider that what Dedekind is trying to do is to give a logical foundation, provide a logical foundation to the concept of number, in particular natural numbers. Well, natural numbers are those kinds of numbers that we consider to be finite, but not all numbers are finite, right? We've got transfinite numbers. So Dedekind needs a way somehow to isolate the finite natural numbers from all of the transfinite numbers, because it's those that he's really wanting to analyze and study and prove theorems about. But he can't do that without a notion of finite. So he can't start with numbers, define finite and infinite in terms of numbers, and then go on to define numbers in terms of finite and infinite, or natural numbers in terms of finite and infinite. Because then we're effectively defining natural numbers in terms of themselves. We get this these circular definitions re-entering into the situation. So Dedekind has opted for a notion of a definition of finite and infinite that is completely independent, completely divorced from the concept of number. And that does mean that potentially, on some level, the definition that he gives may seem to be, it's not quite so clear, in my opinion, how accurately it reflects our intuitive notion of finite and infinite, because we do seem to depend on the notion of number, psychologically at least, to distinguish between finite and infinite. But this definition that Dedekind has given is completely divorced from the concept of number. So to what extent does it accurately reflect our intuitive notion? Now, other authors will take a much more, let's say, inverted commas, natural definition of finite and infinite in terms of numbers. So they'll start with numbers. But the problem that they've got then is that when they're dealing with numbers, they're having to deal with a much more general type of number, potentially. They can't just deal with finite numbers because they don't have a notion of finite and infinite. So they've got what will eventually be the natural numbers, along with all the what will eventually be called the transfinite numbers, all thrown into one big pot. And they've got to deal with a much more general type of number, and then potentially go on to define finite as finite sets. I'm going to talk in terms of sets. Finite sets as those sets which can be put into a one-to-one correspondence with, such and such a natural number, or that has such and such a number of objects or number of elements, for example. And by the way, it might be interesting to note that even though we're dealing, Dedekind's definition is in terms of similar transformations, effectively one-to-one correspondences. The notion of one-to-one correspondence can be defined independently of the concept of number. And if you read Bertrand Russell's Principles of Mathematics, he does just this. He defines one-to-one correspondence independently of the concept of number. So there's no concepts of number kind of sneaking in through the back door or something like that. Now, okay, so just because we've defined something doesn't mean that the definition works exactly how we expect it to. Just because we've defined finite in a way that's in such and such a way that depends on number, where we put number first, and we define finite in terms of number. And then on the other hand, we've got Dedekind's definition where he defines finite in terms of similar transformations. It doesn't, just because these have been defined, it doesn't mean that they both coincide, that they're both equivalent definitions. And there are certain problems with this. So I was reading Václav Šupinský's book a few weeks ago. What was it? Cardinal and Ordinal Numbers. I don't have my own copy. It was a library copy that I was reading, but he was talking about just this issue, Dedekind's definition of infinite and particularly finite. And what he says in that book is that without the axiom of choice, we're not able to prove, or some equivalent to the axiom of choice maybe, we're not able to prove that these two definitions, let's say the natural definition in terms of number and Dedekind's definition of finite in terms of similar transformations, we can't prove that they coincide, that they're equivalent. So what are the consequences of that? What that means is that we might have, on the one hand, a set. Now, again, I'm going to talk in terms of sets rather than systems here. We might have a set that intuitively appears to us to be clearly infinite, an infinite set. But it might be an infinite set that is kind of weird in certain ways, in that it's not similar to a part of itself, a proper part of itself. And it can be proved that no such similar transformation exists. I'm not saying that this has actually happened, but this is a possibility. In the absence of the axiom of choice, this is a very real situation that could arise. So we might have this set that's kind of weird. It's infinite. We can see it's infinite from our intuitive perspective. And according to the natural definition, it's infinite. But when we go to Dedekind's definition, because of the absence of this similar transformation, then Dedekind's definition says that this set is actually finite. So we've got these weird, potentially weird sets of objects, collections of objects, that on the one hand appear to be clearly infinite, but according to certain definitions, the definitions say that they're finite. Okay, the axiom of choice clears up this issue. I haven't gone into the details with it, but I'm assured that this can be done. But this is, so we've got these kind of potentially intermediate sets. You know, are they finite? Are they infinite? Well, it depends on the definition. You know, some sets are definitely infinite, irrespective of the, you know, as long as we've got a reasonably sensible definition, they always come back as infinite. Other sets always come back as finite. But then there's these other ones where different definitions will actually give different responses, finite and infinite. And this seems to clash, obviously, with our intuitive notion that if something is not finite, then it must be infinite, and if something is not infinite, then it must be finite. That we've got this dichotomous situation, and each of these classifications of sets or collections of objects will be mutually exclusive. So a set is definitely one or the other. So how do we deal with this? Well, the literature, maybe around the beginning of the end of the 19th century, beginning of the 20th century, might shed some light on how this kind of issue was dealt with. But so they're just some of the problems that can arise from Dedekind's particular form of definition for finite and infinite systems. So I'm not going to go into any more detail with it here. Maybe I'll go into more detail with it in a different video, but not in this one. So, okay, let's move on. So Theorem 65, there's not really much to prove here, to be honest with you. Every system consisting of a single element is finite. Okay, so if we've got a system S and it consists of a single element, and remember, a system of a single element is to be identified with the element itself. So this was, if you go right back to 2.2 in chapter 1, where Dedekind defines his concept of system, we get this kind of situation arising. So there are two possibilities here for kind of a part of what could be considered a part of the system S. Either we've got the empty system or we've got S itself. Okay, S consists of one element, so we can't have, you know, we've only got these two possibilities. Well, Dedekind has discarded, he's banished the empty system. There is no such thing. We don't consider it. So that's not a possibility for us. So we're left with one possibility. The only part of S is S itself, okay, which is not a proper part. So a proper part must be a part of, if we've got a system S, a proper part would be a part T, such that T does not contain all elements of S. There's at least one element of S that is not contained in T. So, because there is, again, this absence of a similar transformation of S with a proper part of itself, then S must be finite by definition. It's no surprise, really, I guess. Okay, so moving on to the next theorem. So this is another potentially contentious point. Theorem 66, where Dedekind proves that there exist infinite systems. Okay, so I'm not going to say much about this. I'm going to read the text. I'm going to leave it up to you to decide whether you're convinced by this. And not that I want to impress my views, my particular personal prejudices onto anybody watching this regarding this theorem. I personally am not entirely convinced by it, but feel free to make up your own mind about it. So here we go. So the proof of Theorem 66, there exist infinite systems. My own realm of thoughts, i.e. the totality S of all things, which can be objects of my thought, is infinite. For if S signifies an element of S, that's uppercase S, then is the thought lowercase s primed, thus lowercase s can be object of my thought, itself an element of uppercase S. If we regard this as transform phi of lowercase s of the elements lowercase s, then has the transformation phi of uppercase S thus determined the property that the transform uppercase S primed is part of uppercase S. And uppercase S primed is certainly proper part of uppercase S because there are elements in uppercase S, example, my own ego, which are different from such thoughts lowercase s primed and therefore are not contained in uppercase S primed. Finally, it is clear that if A and B are different elements of uppercase S, their transforms A primed, B primed are also different. That therefore the transformation phi is a distinct or similar transformation, hence uppercase S is infinite, which was to be proved. So he considers a very particular system of objects and shows in a certain way that this system is similar to a proper part of itself. Okay, so my personal feeling on this is that it would probably be more appropriate to just assume the existence of infinite systems. I'm not sure that it's something that necessarily can be proved. Maybe I'm wrong on that one, but it's thinking about what goes on in certain axiomatic systems for set theory. It's very common to have an axiom of something like an axiom of infinity. Okay, so we might have something like omega is a set, which is the axiom of infinity. Omega being the set of natural numbers. So, however, Dedekind does think that this is something that is capable of proof. And if we go back to the preface to the first edition of this, in the very first sentence, Dedekind says, "In science, nothing capable of proof ought to be accepted without proof." So, if Dedekind thinks that this is capable of proof, then he's kind of obliged really to provide a proof for it before accepting it. So I personally don't think it necessarily needs proof. I think it could be assumed or postulated. The existence of an infinite set could be postulated and just accepted. But Dedekind thinks otherwise. I'm not saying that Dedekind is wrong, by the way. I'm just saying that my personal perspective on it is that I don't find this particular proof terribly convincing, and I don't necessarily feel that the existence of infinite systems is something that is necessarily capable of proof. Okay, so moving on to Theorem 67. If R and S are similar systems, then is R finite or infinite, according as S is finite or infinite. So in other words then, if R and S are similar systems, then if R is finite, S must be finite, and vice versa. If R is infinite, then S must be infinite, and vice versa. Okay, so he starts with if S is infinite, and by definition, therefore, it must be similar to a proper part of itself. So S is similar to S primed, where S primed is a proper part of S. And R is similar, R and S are similar. So R is similar to S. Then by transitivity, or theorem set 5 or 7. 7. Yeah, theorem 7. Then R is similar to S is similar to S primed. Actually, sorry, no, it's not transitive. That's part. It's 34, is it? Maybe 33 or 34. RNS is similar then. Every system. 33. Oh, it even quotes it there. I didn't even notice that. Yeah, theorem 33. R is similar to S is similar to S primed, then R is similar to S primed. We've also got, where are we? By 33, R must be similar to R, and by 35, likewise, similar to a proper part of R. Right, so, yeah, this is 35. So if we've got a system, I'll use P. A system P and a system Q, which are similar. Just let me get the statements of the theorem right. Is it 35? If R and S similar systems, then is every part of S also similar to a part of R, and every part of S also similar to every proper part of S is also similar to a proper part of R. So if we take a proper part of P, if P and Q are similar, and this is a proper part of P, then it must be similar to a proper part of Q. Okay, so in this case, we've got R and S. So S, R. Here we've got S primed, which is a part of S. And therefore, it's a proper part of S. And therefore, by similarity, this is theorem 35, must be similar to R primed. Okay, so we've got S is similar to S primed by definition of infinite, and the assumption that S is an infinite system. R is similar to S by assumption. So R is similar to S primed. But S primed, being a proper part of S, must be similar to a proper part of R primed. So therefore, R is similar to a proper part of itself, again by transitivity. So we've got S primed is similar to some proper part R primed of R. I mean, maybe I shouldn't use R primed actually, because that suggests that I've that's the transform of R. So let's say T, where T is a proper part of R. So then R is similar to S primed is similar to T, R is similar to T, where T is a proper part of R, and therefore R must be infinite. Which was to be proved. Okay, so theorem 68. Let me just clear a little. In fact, no, I don't really need to clear any space, do I? Okay, I will do actually, because the proof for theorem 68 is on the next page, but I just want to just highlight something with the statements of this theorem. So if you haven't already done so, please feel free to subscribe to the channel, hit the like button, and leave a nice positive comment in the comments section. Okay, so theorem 68. Every system S which possesses an infinite part is likewise infinite, or in other words, every part of a finite system is finite. So there's two statements here, one regarding infinite systems and the other regarding finite systems. So if we've got every system S which possesses an infinite part is likewise infinite, so S has an infinite part, implies that S is infinite. That's the first statement. That's one way that we can formulate the first statement. But then the other statement is like it's kind of the contrapositive of this. Okay, so every part of a finite system, so every system S which possesses an infinite part is likewise infinite, or in other words, every part of a finite system is finite. So if S is finite, in other words, if S is not infinite, then S is finite, this implies that it is not the case that S has an infinite part, or in other words, S has no infinite parts, or in other words, every part of S is finite. Of S is finite. Okay, so really, if we can prove the first of these, S has an infinite part, then S implies that S is infinite. Then we get for free the other statements as well. Okay, so let's have a look at the proof. If T is infinite, and there is hence such a similar transformation psi of T, such that psi T is a proper part of T, then if T is a part of S, we can extend this transformation psi to a transformation phi of S. Okay, so T is infinite, and okay, so I mean, on an intuitive level, this is obvious. This is obvious, right? How could a system which has an infinite part not be infinite? But it has to be proved, right? It goes back to that first sentence and the preface. Anything that is capable of proof cannot be accepted without proof. So we've got S and we've got T here, which is a part of S. I mean, it's not clear necessarily whether T is strictly a proper part of S, or if it could be S itself. I don't see that it necessarily makes any difference, to be honest with you. So then we've got S over here, and we've got psi of T. So our transformation is psi. And psi of T is, because T is assumed to be infinite, then psi of T is psi is such a similar transformation as to make psi of T a proper part of T. Okay, so we've got, this is T here. Okay, so what Dedekind does is he extends this transformation psi from T. He extends it to a similar transformation phi on the whole of S in the following way. So he puts for S in an element of T, he defines phi of S to be equal to psi of S. Okay, so all of these elements of T which got mapped or got transformed by psi into elements of psi T, they all stay the same. Okay, we just rename them as phi of S instead of psi of S. Or if S is not in T, so we're confining ourselves to the system S. So S is not in T, then we define phi S to be equal to S. Okay, so all of these elements that are in S but not in T, we apply the identical transformation to these. Okay, so it's kind of clear how this works. All of the elements that are not in T but are still in S, in other words, all of this region around here ends up here. So where I've drawn the dotted, the dashed kind of line, everything outside of that, but still inside T. T in the original diagram here ends up, oh, I didn't want to do that, ends up in psi of t. But then we've got this kind of, how might you describe it, a kind of no man's land, I guess, between psi of t and these elements of S that are not in T. And let's say, loosely speaking, the boundary of T. It's not really necessarily the right word to use, but that's the word that I'm going to use. So we've got this kind of no man's land. Can I change the colour of my pen here? Okay. So we've got this bit around here. And in here, we have elements of S that are, they're not the transform of any elements from over here. Okay. So they are, as well, in fact, let me continue. Let me continue. Okay, so this transformation phi is a similar one for if A and B denote different elements of S, then we've got different cases that we need to consider. If A and B are both elements of T, so we've got A and we've got B, then by the similarity of psi, psi A and psi B are different, and therefore phi A and phi B are going to be different. Okay. If, on the other hand, we've got if on the other hand we've got A is in T, but B is not, then phi A will end up in psi T, and phi B, so B is up here somewhere, will end up won't be in psi T. So they can't be equal. Their transforms can't be equal. Phi A and phi B can't be equal. If finally neither A nor B is contained in T, then also is phi A equal to A different from phi B equal to B. Okay, because we're applying the identical transformation to A and B in that case. So if A and B started as different elements of S, not in T, then when we apply phi to A, we get A, and we apply phi to B, we get B. Well, if A and B are different, then phi A and phi B, which are both respectively equal to A and B, are also different. So this transformation phi is a similar transformation. Now we need to show that the transform of S under phi, under this transformation, this similar transformation phi, is a proper part of S, which it's kind of obvious really from the diagrams that I've drawn, but let's see what Dedekind has to say. Since further psi t is a part of T, a proper part, that is also a part of S. It's clear that also phi S is part of S, because phi is a transformation of S in itself. And since finally psi t is a proper part of T, there exists in T, and therefore also in S, an element T not contained in psi t, which is equal to phi t. So there's an element, maybe here somewhere, T, which obviously it gets transformed into an element of psi t. But if we look, remember the S's on both sides here, so this S and this S, they're representing the same thing. They contain exactly the same elements. This element T is somewhere in this second version of S. Well, it's not in psi t, but it's still in T. So T gets transformed into an element of psi t, but T is not the transform of any element of S. So therefore, what we find is that the image, that's not the right word to use. The transform, sorry, the transform of S under the transformation, the similar transformation phi is a proper part of S. There are elements of S that are not in phi S. So since then, the transform phi S of every element S not contained in T is equal to S, and hence is different from T. T cannot be contained in phi S. Hence, phi S is a proper part of S, and consequently S is infinite by definition, which was to be proved. Okay, so theorem 69. Every system which is similar to a part of a finite system is itself finite. Let me just clear a bit of space. So every system which is similar to a part of a finite system. So this follows from 67 and 68. Every part. So if we've got a finite system, so let's say S. So this is theorem 69. So S is a finite system, and T is a part of S. In fact, I'll write it a bit more symbolically. T is a part of S, then T must be finite. And this is by theorem 68. And as we saw in theorem 67, any system which is similar to a finite system must itself be finite. So if R is similar to T, then R is finite. So that follows from 67. And that's the proof of theorem 69. Okay, so theorem 70. So this is hopefully I'll be able to make it through this. So I don't have any notes. So it's a little bit fiddly is the proof of this theorem. It's not terribly difficult, in all honesty. It's just a little bit fiddly. So just bear with me on for the proof of this one. Okay, so theorem 70. If A is an element of S, and if the aggregate T of all the elements of S different from A is finite, then is also S finite. Okay, so this is one of the few occasions where Dedekind uses the word aggregate. So I understand aggregate here as being kind of synonymous with part, even though when he uses the word aggregate the first time, it's in section 2 or point 2 when he's defining system. But I understand this as T, the aggregate T, as being a part. It's a system itself which is part of S. I don't know why he uses in particular the word aggregate here, but it doesn't really seem to change very much. But it's just interesting to note that this is one of the few occasions where he actually uses the word aggregate for whatever reason. So intuitively what we've got here then is that if T is a finite system and we add another element to T to create the system S, then S must also be finite. Kind of obvious, but again we've got to verify everything in accordance with Dedekind's definition of finite and infinite. So let's have a look at how he does this. And I'm probably going to have to draw some sort of diagram as we go through this. So bear with me on this one. So we have by 64 to show that if phi denotes any similar, so this applies to an arbitrary similar transformation of the system S in itself, not a particular similar transformation. So phi denotes any similar transformation of S in itself. The transform phi S, or S primed, is never a proper part of S, but always equal to S. So obviously, S is equal to the system compounded of the systems A and T. Remember, a system of a single element is to be identified with that element. We've got. So I'm going to have to draw little circles. So we've got these elements here. These form the elements of T. And then we've got this element A here, which is not part of T. That's an extra element that we add. But these two systems combined are compounded form S. Okay, so that's what we get here. Where am I? And hence by 23, if the transforms are again denoted by accents, so we get from this, if we transform S, we get S primed is equal to the system compounded of A primed and T primed. I can't remember which. Oh, 23, he quotes it. 23, the theorem 23. And on account of the similarity of the transformation phi, A primed is not contained in T primed. If A primed were contained in T primed, then that would suggest that A is an element of T, which it's not by assumption. Okay, so over here, I guess we've got our elements again, and then we've got A primed here. And this is T primed, and altogether we've got S primed. Okay. S prime. Since further by hypothesis, S primed is a part of S. So we don't know what kind of part, whether it's a proper part or whether it's S itself. That's what we've got to try to figure out. We just know that S primed is a part of S because phi is a similar transformation of S in itself. Then must A primed and likewise every element of T primed be either equal to A or be element of T. Okay, because remember S is the system compounded of these two parts, T and A. So if we take an arbitrary element of S, it must either be an element of T or it must be equal to A. Right? And since that also applies to S primed. So if we take any element of S primed, because any element of S primed would also be an element of S, then that element must either be an element of T or it must be equal to A. If then a case which we will treat first, A is not so there's two possibilities. Either the element A is contained in T primed, or the element A is not contained in T primed. Okay, so there's no guarantee. In fact, in general, it won't be the case that A and A primed are equal. In general, that will not be the case. So after the transformation, after A has been transformed, it may be that A is transformed into effectively one of the elements of T. In general, that will be the case. Not necessarily always, as we'll see, but in general, that will be the case. So we treat A is not contained in T primed. Right, so if A does get transformed into an element of T, into an element in T primed, no, A gets transformed, but A is potentially the... I've gone the wrong way, haven't I? A is potentially the transform of one of the elements of T. Right, that's the right way around. So one of these elements in T after transformation by phi will possibly get transformed into A, which means that A will be one of these elements in T prime somewhere. That's the case that we're considering first. I told you it was fiddly, this one. A is not contained in T primed, then must T primed be a part of T, and hence T primed equal to T. So why is that? A is not contained in T primed. Okay, so A is not contained in T primed. So A is, it could be A primed, but it could also be that we've got other elements and A has been transformed into one of these other elements. Okay, so that being the case, then all of these elements of T match up to one and exactly one of the elements of T primed. Okay, I'm drawing it quite suggestively here. I'm not saying that the transformation is as simple as I'm presenting it to be here, but that means that because of the similarity of phi, that T and T primed are going to be equal. Because remember that T is assumed to be finite, right? T is assumed to be finite, so it can't be similar to a proper part of itself. So that's why we get that T primed is equal to T. Because phi is a similar transformation and because T is a finite system. And since A primed, as remarked, is not contained in T primed, then A must be equal to A primed. Okay? Because S consists of T and A. So if we've got S primed, which is a part of S, consists of T primed and this element A primed, which is not in T primed, we know that T is equal to T primed, then the only possibility is that A is actually equal to A primed. And in that case, we get that S primed is actually equal to S. So that's that case dealt with. And then we come on to one that's a bit more complicated, although not much more complicated. It's just, again, a little bit fiddly. So in the opposite case, when A is contained in T primed, okay, let's say this is A here. So now what's happened is one of the elements of T has been transformed into A via phi, and therefore A must be in T primed by definition of T primed. So A is an element of T primed and therefore must be the transform of some element of T. Okay, so it must be equal to B primed, where B is, let's say, this element here. Okay, B is contained in T. We will denote by U the aggregate of all those elements U of T which are different from B. So all of these are U. Then T is equal to the system compounded of B and U. You can see that from the diagram. Obviously, the diagram makes it easier to see these things. Of course, you can't necessarily always rely on the accuracy of a diagram. So use diagrams with caution. And I would say the diagrams that I'm drawing here, take them with a grain of salt. Don't take them too literally. They are really just an aid. That's all they're intended to be. And by 15, S is equal to the system compounded of A, B, and U. Again, you can see that from the diagram. We've got S, which is the whole thing here, which is compounded of T and A, but T is compounded of U and B. So therefore, S is compounded of A, B, and U. And so if S is equal to the system compounded of A, B, and U, then S primed is, by 23, the system compounded of A primed, B primed, and U primed. We now determine a new transformation, psi, and by the way, all of these here, these are going to be U primed. We now determine a new transformation, psi of T, in which we put psi B equal to A primed. So B is going to be transformed into A primed. And generally, psi U equals U primed, which is phi of U. In other words, psi coincides with phi on U. Okay, so psi of U will just be equal to U primed in that case. When by 23, psi of T is equal to, we can see this again from the diagram, it's the system compounded of A primed and U primed. Obviously, psi is a similar transformation because phi was such, and because A is not contained in U. So psi is a similar because phi was such, and because A is not right. Okay, so yeah, so if you check the definition of similarity, it's fine on U, on the part of T which is U, then obviously psi is going to be similar on that part. But then because B is not in U, then then psi B is not going to be in U primed. And that's what we see, right? A primed is not in U primed. So we can kind of intuitively see the similarity. But if you really want to check the details, then check it against the definition. And therefore also A primed is not in U primed. Since further A and every element U is different from B, A and every element of U is different from B. We can see that from the diagram. On account of the similarity of phi, must also A primed and every element U primed be different from A, and consequently contained in T. Right, okay, so yeah, let me clear a bit of space then, because again, T is finite. T is a finite system. So under any similar transformation, and that includes psi, then T and psi T are similar. And consequently, psi of T must be contained in T, because the only element of S which is not contained in T is A. Okay, but under psi, the transformation psi, notice which element gets left out. A, which is equal to B primed. Every other element of S is in T. So all of these elements, A primed, and all of the elements in uppercase U primed, must be in T, because none of them are equal to A. None of these elements are equal to A, and A is the only element of S that is not in T. So psi T, I've got a little bit ahead of myself actually. T and psi T are similar, but psi T is a part of T, and therefore because T is finite and psi is a similar transformation, then T and psi T must be equal. And okay, I need to clear a bit more space again. Bit of a pain. So we've got the system compounded. In fact, it'd be better for me to do it down here. So the system compounded of A primed and U primed is equal to T. So therefore, by 15, the system compounded of A and the system compounded of A primed and U primed is equal to the system compounded of A primed, A, and U primed. Oh, and the system compounded of A and T is equal to the system compounded of A and T. So it's effectively, if I look at each of these individually, each of these systems, and I add the element A effectively to each of these systems. Okay, so remember that A is not an element of T. So I'm genuinely adding a new element here. And A is not equal to A primed, nor is A an element of U primed, and therefore I'm genuinely adding a new element here. But this former is equal to S primed. We saw that earlier. If I can, right, we saw it here. I should have changed the page actually. Never mind. And this latter system is equal to S. That's right from the beginning up here. So in other words, S primed is equal to S. Because phi is a similar transformation, then and it was an arbitrary similar transformation. That means that for any arbitrary similar transformation, S primed will be equal to S. In other words, S can never be similar to a proper part of itself. So we've got S is equal to S primed, and therefore S must be finite by the definition. So I should have changed onto this page. So that's just the end of the proof there. And that brings us to the end of chapter 5. So if there's anything that I've said that hasn't been clear, which I'm sure there are many things, please let me know. If you've got any questions about anything, please feel free to ask them in the comments section or get in touch with me directly. Please hit the like button for this video. Let me know if there's anything that you'd like me to take a closer look at on my channel. If there's any works that you think would be interesting for me to go through. So I've already had a request for Quine's mathematical logic, which I will be getting around to at some point. It might not be for a couple of months yet, but I will get around to that at some point. So it's quite a lengthy work and there's quite a lot to it. But any suggestions, I'm open to any suggestions. Okay, so I'm going to leave it there with this video. The next video, obviously, we'll be looking at chapter 6, Simply Infinite Systems, Series of Natural Numbers, which again is quite a short chapter. So it might be a few days before I get around to doing that. So thank you for watching if you made it this far into the video, and I will look forward to seeing you in the next video.